Good day, everybody. So let's take a look at some sort of foundational and the intro things that would relate to organic chemistry. And then this is going to be the combination of kind of foundational things from organic chemistry and some fundamental items from general chemistry that will help us, hopefully, in our studies of organic chemistry. So I have the loose plan what things we're going to look at. Of course, we cannot potentially go through every possible question and issue and challenge. So this is something that you need to work on and then put your time in by yourself, right? And then maybe have some kind of like office hours, visits and appointments to talk about this issues specific to your studies. And then the purpose of this kind of like video is just to spur your motivation and push you towards the practicing things, right? So that's we are trying to highlight here. So first of all, let's take a look at some fundamental things such as dissociation, charges, and ionized particles, right? So this is the thing that carries over a lot from general chemistry to organic chemistry because very often the ionization reactions of some sort can take place in organic chemistry. So now what we're going to do with is just say, okay, well, we'll have our, let's say, like item one or something like that, right, which will be about ionization. So we'll take a look at some specific cases which can be found quite a bit in organic chemistry. So one of them has something to do with the formation of the water ion, right? Or the hydronium ion, rather. So let's take a look at the water molecule, which looks like this. So it's going to be our like HOH, right? So some things that we can keep in mind is the Lewis structure. So for the water, we'll oftentimes show the two lone pairs, right? And then, by the way, this pattern also will be applied to alcohols, for example, because alcohols will be almost looking like water, except instead of this H, for example, you will have maybe CH3 group, right? I'll just say it right now. So, which is also called methyl in more like specific terms, which we will encounter soon enough, right? So, so the purpose here is just to kind of like see or like make you try to see the connections, right? So between those kind of like simpler general chemistry structures and organic chemistry structures, because essentially the purpose of like all those courses is to build layers of knowledge, right? So you have something kind of like more fundamental, step one, and then in step two, you will see some kind of like elements, pun intended, of step one, which can be used as building blocks to kind of like make stuff in step two, and then kind of like complicate things, right? So like to the better, hopefully. So yeah, if you talk about the dissociation of water, so like some people who were presenting the answers to those questions in the past, they were like correctly using the equilibrium arrows, right? That's another thing to keep in mind, so that it can also be kind of transferred to organic chemistry. And then they would kind of like show the formation of the couple ions, right? Which would look like that. So we'll have here this bond, like with those like big fat electrons, so to say, will be broken, right? And then we can also see or show the arrow pushing, right? So that basically shows that this pair of electrons will move completely towards oxygen, right? And that's it. And then now let's show those like big electrons here. So okay, now charges, right? So we have here originally the neutral oxygen atom. If we look at it this way, so let's maybe make a different color here, red, right? So if you look at the oxygen atom as such, right, with its like surrounding electrons that are either lone pairs or participate in the bonding, so that's going to be our oxygen, right? So with like the surrounding octet of electrons. So by itself, the oxygen atom, as like represented as such, right, will be just an oxygen atom, even if it's bound to other ones. So that's okay, right? So, but ultimately, it will have no charge if we are concerned with the charge on the oxygen. So now what's going to happen is that this arrow shows that this entire pair of electrons will be moving, right? Or kind of another way to like talk about that is that this electron on the right will join the oxygen atom, right? So which will make or which will impart the negative charge on the oxygen, right? So it went from the charge of 0, then it got this electron added to itself, right? So the electron has a negative charge, -1 charge. So you have 0 and -1 charge-wise. So now the total charge will be -1 on the oxygen and this like OH part by extension. So that's how using this example, we can show the formation of this thing, right? The OH minus a particle, if you recall it from the like general chemistry perspective, is called the hydroxide, right? So here you have the hydroxide ion, right? So now let's take a look at some more things. So now as you can see from this like small reaction, you can like take a look at, you can like strike a lot of details, right? Which again, you'll be able to see. So if you're like, paying attention to details, those details will be kind of like replicated over and over again in various organic chemistry reactions that will contain, for example, the dissociation of the OH group, right? This OH group that is now going to be connected maybe to some kind of like CH repeats, right? So the OH group can be also found in like alcohols, right? Not necessarily in water. So water can be used as a proxy, right? So for this talk. So now what we are going to do, like from the water molecule, you are also going to form upon this dissociation, the H, right? Particle, which will be kind of special. Again, so if you look at for example, this bubble, the green one here, so for the H with the dot, that's nothing more than just an atom of H, even though it's bound to the OH piece, right? So what? So atoms can be like forming the covalent bonds, as we know from the past, and that doesn't necessarily like impart a charge necessarily on those atoms. Necessarily is an overused word right now. So, but anyways, so what we see here is like H with a dot, right? It's going to be just a neutral atom of the hydrogen with a charge of 0. So now what you can see here, right, upon this reaction, so this electron technically was lost by the hydrogen, right? And now you are going to form this so-called H plus or the proton ion, right? So proton particle will be formed. So H plus. Hydrogen used to be the neutral atom with a charge of 0. So if if the atom with a charge of 0 loses 1 electron, it loses a negative charge. So technically what happens is that neutral charge, 0, right? Neutrally charged particle with a 0 charge lost a negative charge. So what needs to happen is the charge needs to be balanced, right? So you're going to generate the positive charge instead. So basically 1 negative out, 1 positive in. So that's why we will have H plus with the plus charge, right? So the proton is formed. So just think about like maybe your redox reactions exposure back from honestly high school times, right? So how if the electrons are added, the charge becomes like more negative, right? Because you add the negative charge literally to the particle. So if the electrons are removed, then the charge becomes more positive. So yeah, basically, if you think about like your life, right? So you will add some sort of like negative emotions, then you'll become like more negative, right? So you will carry kind of the negative charge, so to speak, right? So if you let's say remove negative emotions, then you conceivably will become kind of like happy air, right? You'll be more positive. So same happens with the charges of electrons or the electrons in their relationships to like various particles. All right, so we'll have the proton formation. Proton formation can be also like executed in many like other organic compounds. Examples include, for instance, just from the top of my head, alcohols and carboxylic acids, right? So which can be like found in household applications, such as like rubbing alcohol, isopropyl and such, right? Or good old vinegar, right, by Heinz. So anyway, so that's our dissociation of water. So yeah, which is like quite detailed at this point. Charges, loose structures, all set. It's balanced. All right, so now let's take a look at the addition of the proton, right? So the proton can be added to water. So let's say you are going to have some sort of like HOH situation plus maybe HCl, right? So there is going to be the dissociation happening. Also show things which are not necessarily shown, such as the Lewis structures with the corresponding electrons, right, or lone pairs as needed on specific atoms. So now we're going to see the association here. So the H plus will be generated, as we can see, right, because the H again will lose an electron. So, and then here we go. So what's going to happen? So what's going to happen is that this electron rich, obviously, right? So electrons, oxygen will try to get the H plus from HCl, right? And then we'll show basically the movement of electrons with those arrows. So those electrons move towards chlorine. Draw what you see, right? It's going to be chlorine with 1, 2, 3, 4, 5, 6, and then two more, those kind of like big electrons, right? So with the negative charge, you form the counter ion. So now you're going to form another chemical, which is going to be H3O, right? So that's going to be your chloride ion, by the way. Might be like a good term to remember. So now here you have it, right? So here you have what? You have O, H with the original H's. And now this, for example, pair was engaged in the making of the bond with a new hydrogen. Or the proton, right? So that is like a form of hydrogen. So yeah, basically, so this, if you look at this, this looks like, in particular, a pair of electrons, which can be used to make a bond, right? So because again, I was like asking, what's the covalent bond? So covalent bond is made of like two electrons, right? So it's also kind of like made up from the pair of electrons. So yeah, basically now you have this pair of electrons, just leave it alone, right? So you don't have to like use 4 electrons to make one covalent bond. 2 is enough, right? So leave them alone. So now those 2 electrons on the bottom, kind of like they will be shared like so. And now you're going to make a bond, right? You're making a new bond, new OH bond. So that's how it's made. So if you ask me like, why is it made? Well, I'll tell you why. So because these bottom in this picture electrons are shared, and now you have a covalent bond, right? Quite legitimate. Covalent bond, 2 electrons, 2 atoms, all set, right? So now, so this was, right? So if you just kind of like maybe like draw it on the side, right? So once this association happens, you are going to form H plus, right? H plus is like free of electrons. There is no electron literally. So, but now that's why it has like H plus. H plus has a plus charge, right? So, but now you are adding negative electron, right? So one negative charge to the H plus. And now you are making that H with the dot, right? So, which is just a neutral hydrogen atom. So no charge here, okay? But now it's going to be the charge on the oxygen, however, right? So because why? Because oxygen lost one of those electrons. Let's say this electron is now here on the hydrogen, right? So this electron to the left stays here, right? So oxygen lost one negative charge. It used to be a neutrally charged oxygen atom, but now you have 0 charge, and then negative charge is removed, so the positive charge has to be generated. So that's why the H3O plus has the charge, right? So like that's how you can explain it. So all set, you have the counter ion. Now check yourself. 3 H's total. Oxygen, oxygen, chlorine, chlorine. So now we have the atomic balance. All good. So do we have the charge balance? Total charge is here, 0 and 0, neutral, right? Here, if you look at the right side, -1 and +1 total give you 0 as well. So you are all set in terms of the like elemental and the charge balance. So yeah, that's probably kind of like good for now. So for your practice, you can do it with NH3, for example. That's kind of another proxy. So because if you think about it, so why do I talk about those proxies? So like, here's why. So that is NH3, right? So like previously this week, we were looking at the so-called amino groups, right? So which look like that. So if you look at NH3, so you can write it out. So speaking of your previous knowledge that you hopefully do possess, so that's a Lewis structure, right? So like with the lone pair and the bonds are like shown, right? So NH3. So now if you look at the amines, remember, so what we started with is that An example of the amino group could be NH2 with some sort of like organic uh, skeleton, right? Organic chain, carbon chain, as we may call it, using our newly acquired terms, right? So what is that about? So it is going to be NH. So we have a couple hydrogens. So this is going to be your amino group. And now you have some sort of like carbon chain. Let's just make it like one carbon, right? So that's going to be your like shortest chain possible from the carbon atoms, right? You cannot have zero carbon atoms. It's going to be like no carbon chain at all. So, but you must have like maybe at least one, right? So maybe it's going to be a 6, maybe it's going to be a 67, like whatever, right? So the things are like could be infinite potentially. So here we go. So that's now going to be your like amine, right? So if you look at this combination of atoms, so once you have this like carbon nitrogen bond, here. So, and then a couple H's on the hydrogen, you have an example of the amine functional group, right? So, and then if you look at the kind of like connection, so basically you started with NH3 and you ended up with NH2, but instead of the third H, let's say this H here in the circle, it was swapped, right, to CH3. So now, yeah, you have this connection. Okay, well, so that's why you kind of like need to remember, right? So what NH3 is, what, or somebody tells you, what's ammonia, right? Draw me that. And then like imagine, like explain how was ammonia transferred to, or like made, how can theoretically ammonia be made into the amine, right? So, and here we go. From GenChem, you go to Orgo. So from here, this kind of like stuff to that, right? So you have the like amine functional group here, and then this molecule will be called like an amine in general, right? So it's a specific kind of the amine. So yeah, and now yeah, there is like literally actually reactions, right? Chemical reactions that allow you to like perform this transformation from NH3 to CH3 NH2. You go from ammonia, just a general chem compound, right, to the organic chemistry compound. So you have the functional group here to identify, so things like that. So, and then you can like, okay, say, well, there's going to be the lone pair because there is a lone pair on the NH3, right? And then they look similar. So let's like make it happen, lone pair here. So then what else can you say? Well, so if I want to like make it organic, so like make some kind of carbon, right? So what's the carbon like valence, right? So it's going to be 4. So carbon is tetravalent. So it can make maximum up to like 4 bonds, right? So, and then they will, and then carbon will connect to some kind of other atoms, right? With all those 4 bonds. So you cannot just kind of randomly like forget about hydrogen and then just like let it go, right? So it's going to be kind of like looking weird. So it needs to be complete. So here it is complete, right? H, H, H. So, and CN bonds. So you have 3, like 3 plus 1, 4 bonds total. So all good. So yeah, now let's move on finally to, okay, we balanced the reactions. So we'll be looking at balancing a little bit more in detail when we get to the like actual reactions of organic compounds, right? So, but again, balancing. So what's that about, right? So typically we are going to be concerned with the 2 kinds of balance. It's the elemental balance. You need to count basically and make sure that you have, okay, well, for example, here, right? So you have like 3 hydrogens, like 1 oxygen, 1 oxygen. On the left and right side, it needs to be the same number of atoms of a specific kind. So that's what we mean by the atomic or elemental balance, right? We have chlorine atom, all good. Charge, so the charge must be the same, right? Also like on the left and right side of the equation. So total charge, right? So 0, and then here it's also -1 and +1, 0. So that's the kind of like what you need to keep track of once you go through like various orgo reactions. So we took a look at the ionization, so it's pretty nice. So we also took a look at the proton transfer, and then also look at arrows are very kind of like much peculiar to organic chemistry, right? And then they encounter there like to the majority of the times, right? Maybe you did see them in GenChem too, right? When we were showing dissociation of acids. So that's like legitimate topic there. So, but it's more of the rarity, to be honest, in GenChem. So in organic chemistry, it's like very like really ubiquitous, right? It's everywhere. So arrow pushing, that's what it's called. So like be aware of that. Like and then it's just basically showing the movement of electrons. That's like all it is about on a fundamental level. So now let's see. Carbon atom, right? So carbon atom, let's take a look at that. So I'm going to like transition finally to like item two, right? So carbon atom. So like typically what we do is that we're going to be concerned with, again, some Lewis structures, right? So carbon atom is tetravalent in organic chemistry compounds. It means that it can make four bonds, right? And then what you can do, right? So like what we have seen so far, yeah, is the formation of four bonds, right? Total around the carbon atom. So typically in organic chemistry, we'll encounter something like that, right? So basically, so like, tell me what do you see, right? That's a very typical question or request that I can, sorry, I need to get the charger, can make to you, right? So tell me what do you see? So that's a carbon, right? And then it has four bonds, which are just like four single bonds, right? So four single bonds are here present in front of us in this carbon atom. So then what else? Some other possibilities can be made as well, right? So you have like one thing, so then another like a variant, let's say, will be carbon with the two single bonds and one double bond. If you look at this, it's still total four electrons of the carbon atoms are engaged to make four bonds. One, two, three, four, right? So that's all fine. It's not like a single bond, it's a double bond, right? So like two lines close to one another. So last but not least, we'll have this, right? And then you already kind of like review, hopefully, like make yourself review what you have seen this week so far, because we did see those kind of like pieces, right? Or building blocks. So carbon with four single bonds, carbon with two single bonds and one double bond, four bonds total still, right? And then here we have this one, single bond, and we have a triple bond, which kind of like together gives us one, two, three, four bonds total, right? So all good. So this will be kind of like found in like a alkane functional group, right? This will be found in alkene functional group. This will be found in alkyne functional group. So again, so you can kind of like make connections to the further, right, things if you look at those kind of like simple relatively stuff, right? So then more as we kind of like look like it can be even kind of unpacked a little bit more, right? So we can think about the geometry, right? And hybridization of those carbons. Maybe these are familiar terms, maybe not, but yeah. So we will take a look at them. So again, try to ask yourself like in-depth question, like what else can I like see or like tell myself or your like friend, peer, right, with whom you study about this particular like combination or pattern, right, of the bonds around the carbon atom. So where can they be found, right? So maybe draw some like examples of like alkynes with I don't know like six carbons in the chain. So yeah, stuff like that. So yeah, you can kind of like if you try to inquire, so that's kind of like going to be an important skill. Then yeah, you might as well be like in a good shape, not only in this course but in life as well. So because it will like build this inquiry skill that will maybe like help you perhaps like solve some challenges, right? So or create something. So like whatever you're gonna be up to. So it's like all good, right? So inquiry is quite nice. So then now let's move on from the carbon atom with its what's it bonds to the structures, right? So all right. So I'm going to move on to item number three. So item number three. So it is I3 here. All right. So structures. So what do we do? So like we have seen, we started with the like alkenes as our sort of canvas that can be used to draw on like various organic compound examples, right? And here we go. So let's take a look at some like alkanes, right? So alkanes are saturated compounds, right? So that's what we like know about them, and they will contain only single bonds, right? As somebody mentioned earlier this week. So that's pretty good observation. So like item 3, they will only contain single bonds in the structure, right? So they can contain different number of carbon atoms. So also like if you know the number of carbon atoms, you can kind of like calculate how many hydrogens are supposed to be in a particular like alkane, which is not cycloalkane, which is just alkane, right? So cycloalkane and alkane, they're similar, but they have like the words are literally different, right? So one of them is alkane, the other one is cycloalkane. So just pay attention to the details. That's going to be kind of like important. And yeah, there are some similarities, but also there will be like differences between like uh, compound classes, which are described by similar looking words, right? So anyway, for alkanes, so we can like have the general formula CnH2n plus 2, right? You can like calculate how many carbons and hydrogens you have in a particular alkane if you know this formula, right? So let's maybe draw the carbon skeleton in an alkane that would consist of 6 carbons, right? So maybe it's going to be like that. So 4, 6 here. No, it's not 6. Now it is 6, right? So 6 carbons, right? So that's going to be a carbon skeleton. So you typically would draw it like goes like up, down, right? So that's like pretty straightforward. So because it will kind of like show this spatially the tetrahedral, right, geometry of the carbon atom in alkanes. So that's another thing that we can add to this like information plethora about the carbon with 4 single bonds. It is tetrahedral geometry-wise, right, which we can remember probably from the Lewis structure things from Gen Chem. So, and then, yeah, that's why we try to kind of like position the carbon skeleton as such, right? So now, if we draw it like this, right, so those remaining like 4 bonds on this carbon, for example, and any other one, it will now more look like the tetrahedral thing with that like famous 109.5 degrees angle between those bonds, right? So that's what we will kind of like try to represent. That's why we draw it this way, like to show this like tetrahedral representation, right? So then we can show 2 more bonds here, there, more, and here, this guy needs 3 bonds, right? So this terminal atom also needs 3 bonds, right? So now we're going to add hydrogens, so it's going to be pretty straightforward. So each bond will be capped with a hydrogen, and now, yeah, we'll be in a good shape to show this like alkane. So here we'll see some kind of like repetitive building blocks, basically, right? If you pay attention. So we have lots of CH2s, which are kind of like in the middle, right? And then on the edges, so we will have CH3, right? So CH2 makes like 2 CH bonds, and then it makes 2 carbon bonds. So CH3 makes obviously 3 CH bonds and then 1 carbon-carbon bond. So now this is going to be our expanded structure, right? So expanded. So that's going to be called the expanded. So yeah, that's like a very helpful like way. So it could be like a little bit more time consuming, right? All things considered, when you just compare the time it takes to draw all those individual bonds to when you don't have to do that, right? So that's why it's called expanded, right? So you expand the structure of this compound in your drawing type. And this will help because it will help us, for example, in chemical reactions, right? So once somebody tells you, oh, yeah, so like this bond is supposed to be broken, and then you show a squiggle, that kind of like represents the breaking of the bond. The CH bond is broken, right? And then now you know, okay, well, once this bond is broken, so this H is like out, so this carbon stays. And now this electron will be kind of like connected to some other atom, right? So maybe you remove H with a dot, you remove the H hydrogen atom, right? And then you will swap it to like, I don't know, like for example, chlorine atom, right? Now instead of like dot H, you'll have dot Cl with dot, right? So which will stand for the lone pairs on the chlorine. So things like that. So yeah, this will kind of like help you like keep track of like what's happening in the chemical reaction. So that's why those expanded structures are kind of useful, right? So then if we don't want to like show that all that stuff, right? So with the like CH bonds, so we can get rid of that. And then we are going to move on to the condensed structure. So which will look like this. So you have CH3, right? So then you'll have the bond, right? So which still stands for the bond between carbon-carbon, right? So carbon, even though they see like H3 uh, on the way, right? So that's like no big deal. So if you want, you can put also another way to show that. So let me just do that. So you can put H3 here, right, in your condensed drawing, and then you will just show clearly this carbon-carbon bond, but it literally like does matter. So yeah. So anyway, so now you're going to move on to CH2, right? So then we'll have three more CH2s. So CH2. And you see, inevitably, you are going to like kind of like visually have this connection between H and C, but it doesn't matter, right? So like if you know what you're doing, so then you will not say, oh yeah, hydrogen can make two bonds. No, uh, it's not divalent, right? It can only make one bond. So those two H's are attached to this carbon and only and this carbon only, right? So these H's are not attached to that carbon all of a sudden. So and then this carbon at the same time. So this bond is implied to be between carbon and carbon, which is 1, 2, 3, 1, 2, 3, visible here. So that's a carbon-carbon bond. So all good. So then we have a bunch more CH2s. So that's 4 of them. And finally, CH3, right? So this is our condensed formula, basically, right? So then what else? So now we can turn it into skeletal structure, right? So which is also kind of like fine. Okay, those notifications are incessant. Okay, so now it's going to be about bands, right? Or the like vertices in the structure and the ends, right? Which will imply that, oh, there is carbon and hydrogen there, right? At those points. So here we go. Let's see. So maybe we can, like, as we were trying to make it like more approachable. So yeah, basically we would colorize those carbons as like red dots. So each carbon is a red dot. And now here we have like 6 red dots, right? So the bonds will prevail. They will survive in the skeleton structure. Right, but now let's show those 1, 2, 3, yeah, 6 dots, right, like as such. So you don't have to like show the red dots all the time, right? So eventually it will like, okay, you'll be fine, like that you will like tell yourself, okay, well, I know that each end of the line and then each like bend of the line is a carbon with like respective hydrogens in there, right? So but for now, yeah, why not? So as we just commence this stuff, so we can show the dots. So that's our dots right here. So that's 6 of them. No, I didn't count right. So now it's 6 of them. So now we'll switch back to the black ink and then we're going to connect them. So that's 1, 2. So you'll have 6 carbons and you'll have 5 bonds, right? So, and that's it. So that's basically all you need to do for this condensed, not condensed, but skeletal structure, right? So, and then as you can see, so yeah, here, for example, this terminal dot here and this terminal dot, right? So they are CH3. So this dot, as kind of like simple as it looks like, stands for CH3 actually. This one stands for CH2, right? So then what else can we have? So we can also have maybe CH, right? So let's see what CH looks like in the skeletal conformation, skeletal drawing rather. So we are going to maybe, let's say, sacrifice 1H here in favor of another CH3. Let's put CH3 here, right? So now you're all set. You have CH3, tetravalent carbon, 3 CH bonds, 1 carbon-carbon bond. Here we have now not CH2. CH2 must not be there because it would be like pentavalent carbon. Does make sense. So we need to make it CH, right? So if we want to attach CH3 instead of hydrogen here. So now we have CH. So we have the bonds, our 1, 2, 3. We have our bonds, 3 carbon-carbon bonds, and then 1 CH bond. So that's fine. Still, the carbon is tetravalent, right? So now we're going to continue the drawing here. So this is just going to be that, right? And then that's it. So we're going to add 1 more carbon at the end of this line. So because the end of this line will represent CH3, right? So that's the one. That's your CH3 right there. So And now that's it. So yeah, basically, like if you look back at the skeletal structure, you'll be like, what's here, right? So here, so that's still kind of like a band, vertex, intersection, whatever, right? So that's not like just a straight line. Straight line is a bond, right? So that's that means single bond, single bond, single bond, right? So this is like technically like a band of some sort, even though it is kind of like looks like a like three-road intersection or something like that, right? So that stands for a carbon. So here we clearly have the three bonds emanating from it, right? So we can say, okay, well, we make like three carbon-carbon bonds, right, in this case. So now what else can be like on this atom, right? So we know that the hydrogens and carbons are implied, right? So carbons are ends and bends in the structure, in the drawing, and then hydrogens are implied according to the number of bonds that this carbon atom has made, right? So this carbon atom has made three bonds, so we can only add one hydrogen, right, to fulfill the four valences of this carbon. So this carbon here, for example, made two bonds. So which means we can only have potentially, and we do actually have only two hydrogens on this carbon. Only two hydrogens, only two hydrogens. This carbon, and that carbon are all the same as are all CH3, right? Carbons, CH3 kind of like pieces or building blocks. Right, and then so here carbon has only one bond, right? So consequently, so if it can make four bonds, right? The atoms which are not shown are hydrogens. So our logic says us that okay, says to us that we can only have up to three H's here, right? Which is what we actually do have, right? So CH3, CH3, and CH3 again. So maybe like one more case, right, to take a look at is let's draw something like that. I'm going to like remove everything here, clear the page. All right. So, and let's draw something random. So maybe we'll make like a four road intersection here. So that's the one, right? So this is your structure. What is that, right? So here, so let's switch to the red color to track the carbon atoms. That's the one, right? That is your intersection of the like four roads or something. So this is just like end of the line, simple band that's made of like two lines. And that's it, right? So that's your carbons. So now you can count the carbons, right? You have obviously here 1, 2, 3, 4, 5, 6, 7, 7 carbons, right? So maybe let's turn this into the like what's it? Expanded structure, for example, right? So because why not? So and then yeah, this is something that you can also do, just like draw some kind of like a random skeletal structure, right? So make sure that you kind of like follow this tetrahedral geometry, right? So if you look at this, right? So that does look like tetrahedron from your like geometry knowledge, right? So and then yeah, so we have this kind of like down up, down up. So positioning of the carbons. So now let's turn this structure into the what's it called? Expanded structure, right? So each like end of the line and the band is a carbon, but we literally highlighted them. So let's just kind of like turn the red dots into the carbons. So I'm gonna switch back to the ink. So I'm kind of tracing the skeleton. Okay, great. So now what else do we have? So this one, two, let's say this is going to be our second carbon. It has the connection to two more carbons, right? So, and it's going to be something like that. All right, so carbons and H's are not shown, they're implied, right? And then if you know what's going on, then you should be able to show those, right? To yourself or your peer, something like that. So these are our bonds now between the carbons. Okay, great. So now we'll need to fulfill those carbons with the bonds and the hydrogens, right, which are not shown. So here, clearly just one bond was engaged, so we are going to have three more bonds free, right? So three, three free bonds, right? And then three number free bonds, and then here again. Okay, so same thing. So now in those things, those carbons, like two bonds are engaged. So they can only like now make two more bonds, right? So this carbon is special kind of, right? So because all the four bonds are engaged, so no more bonds can be like made from this carbon, right? So you don't want to make it like pentahexavalent, right, or something. So that's going to be not good. So now, what we are going to add, right? So what's not visible is carbons and hydrogens. We have figured out the position of all our carbons. Good. Now let's fortify them, beef them up with hydrogens, right? So it's going to be three bonds. So we can only add hydrogens. So if the atom is not visible, it's either carbon or hydrogen, right? So then here we took into account all the carbons. Now hydrogens move in. The invisible hydrogens will populate the bonds. No bonds here more, no bonds here anymore, no more hydrogens consequently, right? So no hydrogens for you, as they would say in some famous American shows. No soup, no soup for you rather. So that's the one, right? So that's our conversion, right? So now for fun, you can just like eliminate those like CH bonds, right? And then you will have something like CH3, right? So then you'll have the carbon here. So with CH3 on top, CH3 kind of on the bottom, right? So then you're going to move to the CH2 piece, another CH2 piece, and finally here you have like CH3 piece to cap things off, right? So that's the one. We have kind of like a branched alkane. So this alkane, if you look at that, so it contains like quite a bunch of carbons, 1, 2, 3, 4, 5, 6, 7 carbons, right? So now you can maybe draw some isomers from that, right? So that's like one potential compound that we can do, right? So, but conceivably, so like since we can like rearrange the carbons, right? So our nature can do that, whatever, right? So we can make like another arrangement or another arrangement of those carbons, right, in a chain. So maybe we can make it straight, right? It's like straight chain of 6 carbons. So now, or 7 carbons. So now let's try to do that, right? And we'll like try to draw some isomers, right? So that's what we wanted to make happen. So let's try to draw some isomers from this, right? So we can conceivably make quite a bit of them, right? So maybe I missed something, so and then you'll be able to draw more. So yeah, here it is, right? So let's just make like 7 carbons in a straight chain, right? It's straight, but it's not like a straight line. So, but still, it doesn't have any branches. It is just a continuous chain, right? So that's why it's called straight. 1, 2, 3. So 7 carbons, right? 7 carbons. So let's now add hydrogens here. So the bonds, right, between carbons. Okay, good. Hydrogens are coming in. And here we go. So CH2. So if you count the hydrogens, right, so and the carbons in the top molecule and the bottom molecule, it will be the same, right? So it has like the same equivalent number of carbons, equivalent number of hydrogens, right? So like, or equal rather to like one another. So it means that those compounds are isomers, right? So, but for isomers, what we need to do is that they are not identical structurally, right? They're not identical from how the pieces are connected. If you have this molecule and you literally make a copy of this molecule, draw it on the bottom, it's going to be identical molecule, right? So those will not be isomers. It's just kind of the same molecule. Doesn't make sense to be isomers, right? So isomers have something identical and something different. What's identical? Identical is the count of atoms, right? So this molecule has whatever, just calculate like X number of carbons, Y number of hydrogens. This molecule on top also has X number of carbons, Y number of hydrogens. X and Y are the same, right? So X equals X, Y equals Y in the top and bottom molecule. So they have kind of the same number of carbons and they have the same number of hydrogens, right? So, but they have different ways those kind of like carbons, hydrogens are attached to another. That's what makes them isomers, right? So they have the same, in other words, molecular formulas, but they have the same, but they have different structural formulas, right? The way that those molecules are drawn. So yeah, that's it. So that's what we have here for the isomers, right? So now we can potentially make some more isomers. So here we have, for example, the longest chain here is 1, 2, 5 carbons, right? And then we have like a couple like branches stemming off. So from this kind of like carbon here that has like 4 bonds, 4 single bonds, right? No hydrogens. So what else can we make? So let's think about maybe what if we can conceive some sort of like carbon chain that would consist of maybe four carbons. Okay, well, let's see what happens, right? So four carbons, right? But for the isomer, you still need to have the same number, the same molecular formulas, right? So don't just kind of like lose carbons, right? So it still needs to be total in this like isomer which we're trying to draw, 7 carbons, right? So let's maybe make something like that. So we'll make here, right, a branch and another branch. And then maybe let's add one carbon here, right? So now here, so if you look at this very bottom structure, right? So we have our bonds, right? So all good. We have three, 7 carbons, right? Now let's beef them up with the hydrogens. So hydrogens, here we can put 3 hydrogens. Here on this terminal carbon, three hydrogens, 3 and 3. So the interim or like intermediate carbons will have like maybe like CH2 or CH or C structures, right? So here this carbon has 2 bonds, so at max it will accommodate 2 more H's, right? So CH2. So this guy has 3 bonds taken, so let's add one more hydrogen to that consequently. Same here, 3 bonds taken, 1 bond added, right? So you don't have to like, draw all those bonds if you want to like have a truly condensed structure. So I just did it for explanation purposes, but you will have something like that ideally. So like CH here and like CH, right? So maybe draw it here. So yeah, that's fine. So that's your like other like isomer that you made in this case, right? So yeah, so that's what we are going to kind of like be taking a look here. So various like combination, like different combinations, different ways to like of attachment, right? So if you look at some kind of like other molecules, I don't know like what else this can be. Maybe let's take a look at that, right? So like we were previously drawing like a square, right? So which would look like that. Or let's maybe make something like bigger. Let's maybe make like a pentagon, right? So for example, like pentagon will should be looking like this. And then here I'm just like trying to draw the skeletal structure, pentagon, right? So these are all here CH2, 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 CH2 5 times, right? So 5 carbons total and 2 by 5, 10. C5H10, straightforward, right? So like 1 to 2 ratio, basically. So now let's take a look at this structure. What if we draw something like that square? So CH2, 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 but now we're going to make the isomer, right? So like basically like isomer from this to that, right? So how about that? So now are the isomers. So we previously counted C5H10 in this structure, right? Sorry, this is an ugly 0. Okay, so C5H10. Now let's take a look at this. So maybe let's use our famous red color to track the carbons. Carbon, 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 3, 4, and 5. 5 carbons are here, right? So now let's add H's, right? So what about H's there? So, well, that's not a big deal. We can do that. So here it's our terminal one. So it has made 1 bond. Now 3 more bonds are available. H, H, H. So that's CH3 as you see. This one is kind of in the middle somewhere. So 3 bonds are visible here. Make 1 more. So H. 2 bonds, 2 more bonds. H and H. Sorry, handwriting is suffering slightly. So that's it. Count the carbons, 5 carbons. So C5. How about H's? 3 plus 1, 4. 4 plus 2, 6. 6 plus 4, 10. H10. So you see, they are isomers. They have the same molecular formula, C5H10, C5H10, but they have different connections, right? So different ways that those like carbons and hydrogens were connected to make the compound. So this looks like a pentagon. This looks like a square with a like stick or something with an arrow, right? So they're different. So there are different ways to that those carbon and hydrogens were connected. So that's what makes isomers, right? Same molecular formula, but not the same structural formula, which is caused by like various ways to connect the building blocks, right? So here we connected 5 CH2 pieces in a cycle, and we're happy about that. Here we connected maybe like three CH2 pieces, one CH piece, and one CH3 piece into like one molecule. So yeah, that's it for now, I guess. So I need to go somewhere else to the labs potentially. And I thank you for your attention and bye everyone.